Welcome to the briefing to NOAA by the National Academies of Science, Engineering, and Medicine, or NASEM, on its newest report titled Improving Characterization of Anthropogenic Methane Emissions in the United States, which was just published today. Congratulations. My name is David Herring, and on behalf of NOAA's Climate Program Office, I'm going to serve as the Master of Ceremony for today. And I want to thank everyone here in the room for joining us. And I want to thank the dozens of folks who have tuned in our overflow room and in the online group. Before we begin, I'd like to just address a few housekeeping items to orient everyone for how this is today's session is going to go. Please note that with permission from our distinguished guests at the academies and the committee members, today's webinar is being recorded. At the start of today's webinar and throughout most of the event, all participants will be muted to ensure we have good sound quality and with no interruptions. If anyone has a question for the committee during or after the presentation, please enter it into the chat window here in the webinar, and I will be monitoring that window. And at the end of the presentation, when we move into the discussion and question and answer period, I will ask folks in the room if they have questions, and I'll also go to our online audience, so folks will have an opportunity to ask questions if they're interested. I think an e-copy of today's presentation and a recording of this webinar can be posted on the CPO website a little later. So if anyone is interested in getting a copy, I assume that'll be okay. I'm seeing nods, so thank you. We are able to share a copy of this presentation. So as I mentioned today, the NASEM publicly released its report on human emissions of methane in the United States. A NOAA web story has been published about the report, which you can read online on NOAA's main website. And you can also find a link to the report itself where you can download in a PDF copy if you're interested. The report examines current approaches to measuring, monitoring, reporting, and developing inventories of human emissions of methane to the United States, into the atmosphere. This matters because methane is the second most prevalent greenhouse gas emitted in the United States, and its abundance in the atmosphere is rising in large part due to human activities. The new NASEM report was requested and sponsored by the Environmental Protection Agency, Department of Energy, NASA, and NOAA. Specifically, within NOAA, the report was co-sponsored by CPO's Atmospheric Chemistry, Carbon Cycle, and Climate Program, or AC4. And we're joined today by both Dr. Ken Mooney and Monica Kopacz, and I would like to welcome and invite Dr. Mooney to say a few words on behalf of the AC4 program.
Yeah, I'll be brief. I just want to thank the committee for a really great report. A lot to chew on there, and it'll take us a while to assimilate and react to it and everything like that. But we certainly do appreciate your efforts. It's actually a great report. And the one thing that I liked about the report, and I assume this is mainly due to the committee, is that it's a readable report. So it's not something that you put a good job of putting it together in a very readable form. The other thing I want to do is thank the Academy for working with us on producing that report. We have a long history with the Academy, going back all the way to the days of GARP, which precedes most of the people in this office, and then into WCRP and now USGCRP. They have been a strong, loyal partner working with NOAA. We certainly do appreciate that, and we hope that in the future we have even more elaborate interactions with the Academy. So that's all I wanted to say, was thank the committee, thank the Academy for producing the report.
Thank you, Ken. So I wanted to greet and welcome Dr. Amanda Stout, Director of the NASEM's Board on Atmospheric Sciences and Climate, so welcome. And Katie Thomas, Senior Program Officer for the board. Thank you for joining us here at NOAA, and congratulations again on this new report. Now we're ready to hear from the NASEM's Committee on Anthropogenic Methane Emissions in the United States. I'm pleased to welcome and introduce Dr. James White, who serves as the committee chair. Dr. White is the Interim Dean of the College of Arts and Sciences at the University of Colorado Boulder, where he is also a professor of geological sciences. So welcome, Dr. White. He is joined by three other committee members today. Dr. Gene Bogner, a research professor at the University of Illinois at Chicago in the Department of Earth and Environmental Sciences. So welcome, Dr. Bogner. Mr. Fiji George is the Director of Strategic Solutions at Southwestern Energy. He has more than 23 years of experience related to energy, environment, and sustainability issues. So welcome, Mr. George. And Dr. Stephen Wofsy, Professor of Atmospheric and Environmental Science at Harvard University. Welcome, Dr. Wofsy. Now I'd like to hand it over to Dr. White to begin today's presentation, which will run about 25 minutes or so. And then afterwards, there will be time for Q&A and discussions. And again, if anyone has questions, you're here in the room, just raise your hand. If you're in the GoToWebinar, just put it in the chat window and we'll get to them as time permits. So Dr. White, Committee Chair, the microphone is yours.
Thank you so much, David, and thank you, Ken, for hosting us here. On behalf of the board, I'd like to thank NOAA for supporting this study and for the years of interactions between NOAA and the National Academy over the years. And we've seen each other at many meetings over time. Yes. So what I'm going to do is give you a brief introduction to the report and then turn it over to Steve and to Jean to talk more about our recommendations. So are you advancing slides? I will. I'll just click you.
Just make that go. Maybe I need to actually click in there and then we go.
Okay. So I won't dwell on these very much because this is something that all of you know about. Why measure, monitor, and track methane? It has numerous interactions with human beings, which make it a really interesting gas from that perspective. There's certainly climate impacts. It's one of the most potent greenhouse gases. It is part of the economy. It is natural gas. It is capturable from natural gas petroleum wells, as well as from landfills and manure management and other areas. It has human health impacts. Methane contributes to ground level ozone pollution, and ground level ozone pollution is one of our primary health issues. And it has safety overtones as well. It is flammable, it is dangerous, and not only, as it says here, within mines, but anywhere where you have sufficient amounts of methane being produced, it can be a serious problem from a combustion point of view. Next slide, please. Again, I'm not telling you anything you don't already know, but the orange arrows here are the anthropogenic fluxes broken into fossil fuel and ag and waste. I would point out that enteric fermentation, that cow there, is your #1 anthropogenic source in the United States. Biomass burning contributes both from the anthropogenic side and from the natural side, but this slide also points out that there's a considerable natural component to methane. So the green arrows, wetlands, other natural emissions, geologic, termites, oceans, permafrost, etc. Roughly 40% in the United States of the methane production is natural, which makes this an interesting gas from that perspective. We have to understand the background. And certainly NOAA plays the primary role in understanding the background of methane and where that comes from. I'd also point out on this slide that wetlands, while it's green, probably ought to have the same color as biomass burning these days because of climate changes impacting particularly large rainfalls and the impact that human beings have on wetlands, both in terms of artificially creating them and purposely making them go away. The dominant sink is hydroxyl in the atmosphere, and right now methane is growing, so the dominant sink is not keeping up with the sources. Next slide. The committee focused in on the approach to methane monitoring, and again, not a surprise here, looking at both the bottom-up and the top-down approaches. So the bottom-up approach being what it says here, individual source measurements, ranging from individual valves on a petroleum extraction operation to individual cows, up to facility-to-site measurements, and the change in technology in terms of measuring and monitoring systems has allowed us now to be able to put a system in the back seat of a car and drive it around. That's something that has changed. And then going up a little bit higher into aircraft sampling and tower measurements, part of the NOAA baseline system, but also part of NOAA's purposeful monitoring of North America. And then up a little higher into satellite retrievals. And at the moment, satellites, while they can cover the globe, cannot do so with the same kind of accuracy, with enough accuracy and precision to really be the dominant atmospheric monitoring. The dominant atmospheric monitoring is today still NOAA's network between the surface samples, the airplanes, and the tall towers. Next slide. So bringing together the top down and the bottom up is really the central focus of the committee's report. The bottom up development, so in terms of strengths, this is obviously where you can get in and actually measure specific sources. You can measure if you've got leaky valves, if you've got manure piles, what kind of, if you've got landfills, what kind of magnitudes are there. Limitations is obviously that you can't account for all sources. It's impractical to measure everything all the time. And so we tend to measure what we think are representative things and then extrapolate. And it's that extrapolation that adds uncertainty. It also says inaccurate, but it's basically, this is part of the problem of how do you do bottom-up work. And so the next slide. That leads us to top-down, and top-down and bottom-up are obviously complementary. And one of the, I'll get to sort of presage what Steve is going to say, but basically the gold standard here as far as science goes is, can you measure bottom-up and you measure top-down and get them to agree? And if you can do that, then you've got a dense enough bottom-up network, and you've got a dense enough in time and space top-down network, which we don't have today in either case. The strengths are you can include emissions from all sources, so that airplane is sampling air. It's not going to miss a source at the surface. That's practically impossible. But on the other hand, you have to be able to attribute what you see at 10,000 feet back to what the footprint was at the surface, and what fluxes contributed to that methane in the atmosphere. The next slide. There are a number of inventories that exist. The most famous, if you will, is the greenhouse gas inventory, the GHGI. That's the main U.S. inventory of anthropogenic emissions. It is required by treaty between the U.S. and other countries via the IPCC. It's national annual resolution. It serves its purpose as its inventory, and there are other inventories that serve their purposes as well. What the committee is calling for in this report is an amped up version of the GHGI, if you will, something that has the temporal and spatial density to be able to really answer a lot more questions. That's not to say that the GHGI or the other inventories that exist, for example, California's inventory, are not really excellent, hardworking, producing inventories. It's that in order to really cover the U.S., we have to be even more purposeful in terms of measuring and monitoring in time and space. Next slide. Why this study? Methane is the second most prevalent greenhouse gas emitted in the U.S. It is easily the greenhouse gas that has the biggest human footprint on it, other than maybe the gases that the Earth never created, like CFCs. It's gone up by about 250%, and CO2 and N2O at about 30%. There are certainly concerns these days about the expansion of natural gas leading to methane emissions. That's true not only from a reality that we see a lot of additional natural gas extraction, but from a public perception point of view, which CG can speak to, has impacts in terms of how people view companies and how they invest in companies. There are, as I pointed out before, numerous new analyses of methane emissions, numerous new techniques. The same kind of technological advancements that have fueled that little computer you have on your hip or in your pocket have also changed the way that measurements are made. There are now, for example, methane measurements on a chip that can fly around in a drone. So maybe not with the same kind of precision that you want, but maybe the day will come. And there are discrepancies between top-down and bottom-up approaches, and that has certainly fueled the discussions that have existed out there. So next slide. This is just a statement of task. I will skip over that. It says we should understand anthropogenic methane and study it. Next slide. I will point out that committee members here, I'm not going to read all the names, but I would point out that the composition of the committee mirrors the interdisciplinary nature of methane. We needed on the committee representatives from petroleum gas. We needed representatives from the agricultural community and enteric fermentation. We needed representatives from the landfill community. We needed representatives from the atmospheric community. And so as they're now very tired of hearing me say, the first couple of meetings we had some really interesting cross-purpose discussions because we weren't all speaking the same language. And the committee, however, came together really well around a common vocabulary, around a common problem, which we hope is what happens also as this report is released. So next slide. And then this is the big take-home poster from the report. It talks about an amped up, an enhanced, a larger and better atmospheric monitoring system with a larger and better surface monitoring system to the point where these two can form a linked circle, where you can indeed verify what you see you can estimate fluxes by two different independent methods, and that's the gold standard. So the next slide. Then I'll turn this over to you, Steve.
Okay, so the recommendation number 1 of the committee pertains to observations and interpreting the observations and should be especially relevant to the group here at NOAA. So recommendation number 1 says that NOAA and NASA should continue and should enhance current atmospheric methane observations and should advance models and assimilation techniques used by top-down approaches. So I added the should there to be clear that those are 3 separate imperatives in our recommendation. And it reflects the fact that observations are the foundation for any understanding and for any actionable science. And so, NASA's observations have their proper space in the heavens, and NOAA's really pertain to the atmospheric in situ observations largely, and NOAA has played a very critical role up to the current time, and we'd like to see that strengthened and expanded. So if we go to the next slide, please. So the current network is kind of bullets here. It's spatially and temporally sparse. Well, okay, that's going to be true for any network anytime. But I think in terms of the goals that we have for understanding and inventorying and providing policy tools for methane, it's notably sparse. Much better than it was 15 years ago, and we hope to see it much better 15 years from now. So to strengthen the observations, we would need a more frequent and denser network of observations. You can imagine making a very good case for twice as many tall towers, for example, for more routine aircraft profiles. And the data collection strategies need to account for the temporal and spatial variability as it will be needed to make a gridded inventory that actually does the job. And so the linkage here is going downstream from this recommendation 1 to the other recommendations. And the observation system, simulation experiments and field experiments and all of this really pertain to the question of making this stuff usable at the next level, at the level of the inventory. And so we see NOAA and NASA as the observation agencies and really playing a critical role there. And I should add that in the past, a lot of progress has been made. Like I say, I can really look back over the last 15 years and say, wow, this has really come a long way. And a lot of this has been done in partnership between the agencies and between the agencies and private sector individuals, the universities, more recently with the oil and gas companies. These types of partnerships in this endeavor, I think, are really key to making it work to be really usable and to be most innovative. May I have the next slide, please? In terms of strengthening modeling, I've already kind of spoken to this. If we look at current inverse model estimates for how much methane is coming from the oil and gas sector, for example, in the United States, they range over a factor of 2 or so. And so we really need to have observations that allow us to pare that error budget down and to be able to actually make some definitive statements about what the trends are and what are driving the trends. In order to do that, we will need to use and develop more accurate prior estimates. So there's a two-way street here. The next one is inventory, so that would be your prior estimate, and then better transport models in particular, and better techniques for model evaluation. And when it says freely share data so the researchers can evaluate the effects of using various data sets, it really goes beyond that. It's not just a question of sharing data, but it's making the data usable. It's reaching out to the community to encourage people to make critical assessments with these data. It does a good job of this, but it's not right now. If you want to, let's say, take a focus on methane and start to go and look for all the data and look for the models and look for the data that went into the models, whatever, you're going to spend a long time looking around the internet for that. And in the end of the day, you're going to find that maybe you didn't get everything you needed or it wasn't all internally consistent. May I have the next slide, please? Multi-scale observational strategies. This is really a very big deal. This is also something that has been pioneered in NOAA to a large extent. But so these things all fit together. You learn different things from the tall tower network than you learn from the aircraft vertical profiles, and different again than what you learn from remote sensing and whatnot. And all of those are needed if you're going to use this in the next step in developing inventories that are actually providing actionability or enabling people to make this science actionable. And so it supplies, in addition to multi-scale, I would also say multi-species. So other things that go along with methane and methane isotopes can and should be part of the strategy. So may I have the next slide, please? So now we will go over to recommendation number 2. So the idea for recommendation number 1 was to provide the raw material so that EPA and potentially the other agencies can construct fine-scale, spatially and temporally explicit gridded inventories. Now, when we talk about gridded inventories, one of the questions that arise right away is, well, what are you going to do with it, and why is it important to have that? And I'm not going to focus too much on that right here. That is maybe not the real focus for NOAA, but the real focus here is, okay, how do we take that stuff that we just talked about in recommendation number 1 and actually make it usable so that these inventories can be used for the various policy and scientific purposes? May I have the next slide, please? So right now we have the greenhouse gas inventory. It's a very good inventory from some standpoints. If you look at it in terms of international competition, it's not bad. It's highly aggregated, and it's not really testable because it's at the national scale, annual scale. You can't make measurements at the national and annual scales. So the gridded inventory, at the very least, is needed to be able to create a version that is testable. Then it also has all kinds of applications, which I'm not going to go into very much. But just as an example, when we did some work in Massachusetts to show how much natural gas was being lost from the systems around Boston, that led the state to change its policies on what ratepayers would pay for to repair infrastructure. So it's something that people had been trying to accomplish for 20 years, and that atmospheric study catalyzed that finally they could get it done. May I have the next slide, please? Oh, I'm sorry, please go back for a moment. The last point there, verifiability is the bedrock upon which inventories should be built if they are to be widely applicable to policy needs. Basically, what that means is people have to be able to be sure that they know what the heck they're talking about. They don't know, they don't believe it, they have things varying over a factor of 2. How can you see whether there's a trend if you can't even measure to a factor of 2? So that is really the hallmark here. May I have the next slide, please? Okay, so I guess I've already talked about this a good bit. Take the next one, please. This just points out that within the recent years, like in 2016, the first specialized U.S. inventory for methane that was gridded came out. This Moskers study by Bram Moskers and Daniel Jacob and their collaborators. It's at a fairly high resolution, 1 month temporal resolution. It's a one-off. There are no current plans, as far as I know, to do it again. So this is clearly a problem. It should be something that is continually improved upon and continually brought forward. And there are a number of obstacles to that, which I think we'd like to see broken down, and so that we can actually develop these as the tools to be used. If you compare the monsters to the maybe previous gridded inventory, that really wonderful product called Edgar from the Netherlands uses proxies of various sorts to get global gridded. It's really beautiful. You compare those two, they don't agree at all about where the emissions are. And so that's clearly a problem. And so it tells you right away that you've got a lot of work to do. May I have the next slide, please? Okay, Jean.
Recommendation number 3. EPA, DOE, NOAA, and USDA should promote a sustainable process for incorporating the latest science into the U.S. greenhouse gas inventory and regularly review U.S. methane inventory methodologies. We view the inventory process as an evolutionary process, wherein as the science develops and becomes better and better informed by both bottom-up and top-down measurements, that the inventories can contemporaneously improve. Next slide, please. How do we do this? It's certainly true that many inventory methodologies currently do not reflect the state of the science. The U.S. greenhouse gas inventory also maintains the need to backcast to 1990, which is a bit of a constraint. And we suggest that an advisor group, a multi-agency advisory group, also composed of experts from academia, industry, policymaking, NGOs, could be formed to help advise how new science could be incrementally incorporated into the whole greenhouse gas inventory process. Next slide, please. This is a view of the committee's review of the current inventory process. Certain sectors, petroleum, natural gas, enteric fermentation, manure management, and landfills, require some additional focus because of their high uncertainties. We tried to assess confidence in the current greenhouse gas inventory estimates, and you can see that coal mining, which is particularly from underground mines and ventilation systems, has a relatively high certainty compared to the other sources which I just mentioned. So there's a prioritization that can be done with respect to concentrating on certain sources before other sources. Next slide, please. If we look at petroleum and natural gas systems, do you want to speak to this one? Okay. Uncertainties, certainly temporal and spatial variability, sparse activity data, despite the abundance of emission sources, presence of unaccounted for emission sources. There's known knowns and unknown unknowns. To reduce uncertainties, probably a better characterization of high emitting events is a practical thing to do through more intensive field measurement studies at various temporal and spatial scales. Supplement the greenhouse gas reporting program data with public records, and update characterization of emissions from key sources that still rely on, surprisingly, emission factors from the 1990s. Next slide, please. Coal mining. Uncertainties include mine ventilation measurements, which are not confirmed by emission measurements at the surface, and what is emitted from abandoned underground mines and surface mines are basically calculated currently based on the coal gas content. Emission factors tend to be state and region-based and may not be accurate at the smaller mine scale itself. To reduce uncertainties for mines, require and implement measurements at entries and emissions at the surface, update and increase the reliability of the gas content data, and for abandoned mines, improve monitoring on those abandoned mines, including pressures and concentrations. Next slide, please. Unaccounted for sources, these are known unknowns. Certain things sources may not be fully accounted for in the current inventories. Residential, commercial operations, post-metering is a is a big issue which has arisen. Also previously unknown sources that have been unrecognized because of their scale, complexity, and other factors. To reduce uncertainties, we need to increase measurements of sources, which we currently ignore or we assume are negligible based on probably a limited database of screening studies, and to improve the integration of top-down and bottom-up measurements. Next slide, please. Himitting sources. These have arisen in a number of papers, particularly from the oil and gas sector, where a very small number of sources emit a large number of the total emissions. They've been called heavy tails, super emitters, but these are incredibly difficult to try to incorporate into the regular greenhouse gas inventory process. But they are very important to gain a more mechanistic understanding of these sources and establish appropriate estimation methods and methods for statistical analysis and statistically valid consideration of the magnitude of these sources. Next slide. Recommendation number 4. The U.S. should establish and maintain a nationwide research effort to improve accuracy, reliability, and applicability of anthropogenic methane emissions estimates at scales ranging from individual facilities to gridded regional national estimates. We believe the gold standard is the gridded inventory, which is needed to link the bottom-up and top-down measurement strategies and move forward in an integrated program to improve our understanding and our projections for methane emissions. Next slide. I think I've probably said some of this already. Emission inventory improvement studies should incorporate multiple key features, bottom-up, top-down measurement campaigns, which are strategically conducted for a variety of sources. Sampling strategies to account for these infrequent or rare high-emitting events and sources, and certainly operator participation to provide access to sites and enough knowledge of the operational details that we can pin down the mechanics of these sources. Also, data collection strategies to account for temporal and spatial variability, and certainly comprehensive, up-to-date, spatially temporal resolved estimates from all source categories. Next slide. How do we present methane emissions data and results? Certainly, data are generated by various entities and diverse stakeholder communities that need to use these data. There are common approaches to facilitate the presentation of these study results for multiple uses. The research networks that help standardize clarity and scope, spatial and temporal boundaries, need to provide data on mass time basis and intensity metrics, and certainly increased data transparency is important by making the underlying report data publicly available, as Steve was alluding to in his remarks previously. Next slide. Way forward. Here's our take-home slide. You see the gridded inventory between the top-down and the bottom-up strategies for methane emissions for the United States. Progress is required on each interlinked recommendation to address this challenge, and we believe that as this process moves forward over the next several years, that the implementation will improve our quantification and attribution of methane emissions and trends, and certainly help identify knowledge gaps and guide avenues for improving the methane emissions inventory process for the United States. Next slide. And we thank the members of the committee, graciously thank our National Academy of Science sponsors and overseers, Katie, April, and happy to answer questions. The report is now publicly available as of a couple of hours ago.
Well, again, congratulations and thank you. Thank you, Dr. White and Dr. Wassi, Wagner, and Mr. George. Maybe I'll get things started. I have a question. I'm sure folks in the room do and folks online, but maybe just to get the ball rolling, I'm not sure if this is best directed to you, Jim, or you, Amanda, but who is this report for, and what do you hope or envision they will do with this information?
I think the report has multiple audiences. From a broad perspective, we hope that certainly the government agencies, all the way from federal to local, will take our call for a better understanding of methane seriously. Human beings have a really large footprint on the planet. We are the major agents of change, and we don't, quite frankly, take that as seriously as we probably should. We should have a much more robust understanding of what we are doing to the planet. So on the macro scale, I would hope that this helps to catalyze a different relationship with the environment, with the planet. And then all the way down to the granular to the small level. It's been a long couple of days. All the way down to the small level, where we know that a gridded network verified by top-down measurements can help identify potential missing sources, can help quantify emissions far better. Numerous examples of where Skiamaki found a bunch of methane coming out of the Four Corners area that we didn't know about before, to when measurements were first made in California, the expectation was that the oil and gas industry was the #1 emitter. It turned out to be cows. So until you actually measure, you don't know what you're going to find. And it's when you are measuring that you can take good policy action and good action at the local level.
Thank you. Amanda, was there something you wanted to add?
Well, sure. And I'll speak more from the sort of role of the academies and sort of how we think about these reports. And certainly at first level, we hope that it's useful for you all and NOAA. You guys sponsored the work, and we hope that we've given some thought to the types of questions that you guys struggle with and provide some input on those, as well as to the other 3 sponsors who are NASA, EPA, and DOE. We also did briefings on the Hill yesterday, so we know there's some congressional interest in the report, so that's another audience that we definitely think about. And then we are likely going to look to present this report at scientific conferences and sort of help stimulate a discussion within the scientific community. We actually have 2 other reports coming out in the next 6 months that are also dealing with aspects of carbon. One on carbon dioxide removal and sequestration, and another one on carbon utilization. And so I think there may be an opportunity to start to kind of have a conversation about all these pieces fit together as well. So that's another thing we're thinking about down the road.
Excellent. Thank you. Let me open it up for my colleagues in the room to see if others have questions that they would like to ask. Wayne.
Yeah, David, thank you. I, too, want to add my congratulations to the committee on behalf of the NOAA Climate Program Office and to the Academy for the continued outstanding work. I actually want to raise a question that I brought up yesterday at the agency briefing in a slightly different way, partly for, I hope, for the benefit of the NOAA listeners, but actually also to maybe help me understand a little bit better. So I think many in NOAA can appreciate the value of a gridded inventory for many purposes. And there's a lot of practical issues that come up immediately. So from that perspective, of course, we have budget limitations. And I think it would be very helpful to better understand, again, I want to use this term, what is the 100% requirement? And by that I mean, how fine is fine enough? Which users are we really going after to meet their needs? The national approach, and what is the role of the federal agencies and the private sector? We talked briefly about the weather analogy, and I thought a little more about this, actually having been in the Weather Service for 20 years and maybe have a little bit of background there. And it's not always true that by going to higher resolution you get a better forecast. In fact, if you don't know the underlying physics and it's not represented well in the model, then you don't necessarily gain by doubling the resolution. So I think from that perspective, I'd love to hear your views on what observation, would be best suited to going after this merger of the top-down and bottom-up, among other things.
Well, let me address that last bit, and I'm sure my colleagues have comments as well. I think you actually put your finger on what the committee is really calling for, which is improvements in both the top-down and the bottom-up. And we don't feel as though improving one without the other is the way to go. Because you cannot so oversample the surface that you answer all the questions any more than you can so oversample the atmosphere that you can answer all the questions. And I think it's that the complementary nature of those two approaches. I mean, I think the weather analogy, as I've thought about it over the last time, I'm kind of liking it now. Yes, I mean, if you increase the number of surface observations, you don't necessarily get a better forecast. You've also got to deal with the top down in that case. You've got to do the better modeling. You've got to put that physics together in the atmosphere better and use all that input data. So really what we're talking about is a better surface gridded system that can give you that basic data and a better top down with better modeling and everything else that you need to go along with that. And we feel as though, I keep losing my name tag, we feel as though, this audience, NOAA, you are the primary agency when it comes to the particularly the atmospheric measurements. And that's, we feel as though is extremely important that those measurements be continued and expanded. And it is, we understand, that you're the one that sort of figure out where all the budget issues come from. But, if you need us to say, to Congress and to other agencies, you really should pay more attention to this, then we are happy to do that, because I think that's really important. We're not going to have a much deeper understanding of our relationship with the planet until we're willing to spend a little more money. I don't know if this is still true. I'll just tell you this: I lecture to 1,000 level students, but a few years ago I looked this up. The U.S. spends more money on movie popcorn than it does on monitoring the planet, which is, that's sad, right? And so I do think that there's both going on, and I'll let my colleagues jump in.
Yeah, I'd like to comment on. So the NOAA has a long and distinguished history in this area, and if you wanted to address the question in a really systematic way, you could do a study that essentially asks the question, which observations provide the most value to the overall enterprise, defining the overall enterprise as you would in here. Some of the things that you might think about is that the atmosphere, the three-dimensionality of the atmosphere plus the time domain makes a challenge for you. And so you could think about ground-based remote sensing, which is definitely possible now. It may not have been possible 10 years ago. You could say, what happens if I put such sensors at all of my tall towers? What benefit would I get from that? That would just be an example. Or another example would be, if I make all of my measurements continuous in time versus weekly or daily measurements, what benefit do I get from that? And each of those, you can see, they would contribute. Now, then you do a cost-benefit analysis through study tools that you have in your laboratories and in your collaborating institutions. You could ask that question, you could get an answer, and you would know which ones to go after. And I think that you have a really unbelievably powerful foundation on which to build. And so you could decide how to build on it now with tools that didn't exist 5 years ago. And I really would urge you to consider doing that.
So let me add just one more point following up on what Jim and Steve mentioned. In the annals of methane focus over the past 5 to 10 years, there are two papers that brought this to light, and I won't talk about the first one from Cornell, but the second paper was from Gabby Petroleum's work in 2012. That was the one that brought up, hey, there is an issue with oil and gas. What is NOAA plays at the space, if we look at our poster, the middle space. Sometimes it's top down, sometimes it's bottoms up, with Rushnell's team and the ACREP, Gabby and Stefan and others. And, they've also tried to get some form of gridded inventories established for their area of measurement. So what I'm trying to say is there is a wealth of knowledge and past experience that NOAA brings in. It's a matter of focusing and working with the communities of interest and also the other stakeholders, especially EPA, DOE, and when collectively focusing your strengths and focusing on a single mission that you can prioritize. And I think we mentioned, somebody asked us a question, how long is this going to take, and it is a process. We're not saying, well, you got to do it next year.
Go ahead. Okay, I'll just make a small point here. I think because there's been an explosion of new methodologies, techniques, instrumentation over the last decade or so, I think there's a need for more multidimensional studies using a variety of techniques at various spatial and temporal scales for specific sources so that we understand those sources. And then I think there's also a place for what you might call process-based models, which take the results of those techniques and develop appropriate inventory models, which are at which achieve more sophistication than, the inventory methods that we're all familiar with, which are based on emission factors, that can actually look at temporal and spatial variability. And some sources like I work with in the landfill sector, which actually have a climate feedback through soil oxidation, and that requires models.
So yeah, just one other point I wanted to make is that although we don't touch on it much here in the report, when you enhance your observational network, you can attack a number of different environmental problems that go beyond methane. So you take methane as your focus, you say, what else would I like to measure? Maybe I need CO in here, and CO2, and ethane. And all of a sudden, without breaking the bank, you're actually contributing to and attacking a number of different problems at the same time. A lot of times you say, well, if I make more of these, more dimensionality, then I'm adding more unknowns and I'm adding information, but I don't actually think that's true for methane. I think for methane, those things can actually be very synergistic, and it would be another thing to think about if you designed a study to assess, okay, what is our optimal build out?
Arlen.
Hi, Arlen Andrews from NOAA DND. You may know that the National Weather Service has a commercial aircraft monitoring program for water vapor that has 157 aircraft equipped with really high-class spectrometers. It gets about 1,000 profiles a day over the U.S., and in contrast, our NOAA GMD network that was shown here gets about 30 profiles a month. So 1,000 profiles a day versus 30 profiles a month. I feel like with that kind of data, there wouldn't be much room for model physics errors to hide. I'm curious what you think that such data might add or not.
Change the landscape like an earthquake? Small impact.
I think that's a good example of the kind of thinking that we need to bring to bear on this problem.
Exactly.
And we call for, just that kind of thinking when it comes to both the atmospheric side and the surface side. I think if we put the kind of effort into the problem that the problem requires, we would advance this field tremendously in a short period of time.
Yeah, I think what Arlen was talking about would then get you thinking about technology. So I don't think of a current sensor for methane that you could plug into something like the water vapor, but we're not far off.
Nope.
So maybe you say, okay, let's give a push and see if we can get some competition amongst instrument designers, make something that would work and it could be certified.
I have another question that might take us slightly outside the scope of the report, but I'd be curious to see if you'll entertain it. We sometimes read and hear that there's concern that there can be tipping points in the system, that there could be an abrupt change, such as certain sources where we might see a sudden or relatively sudden increase in the emission of methane, say from methane hydrates in the ocean or from other places. I'm curious to know if the committee shares this concern. Is this a valid concern that there could be some abrupt change? And if it were to occur, do you think we would be able to detect it in a timely manner? And is the system and the approach that you're calling for able to address?
Can I take that one?
You can start.
So I think the methane hydrate question has come up in every single one of these, and I just lectured my class on this matter in the last week. So methane hydrates do not exist in stable form at the surface. They have to be under about 20 atmospheres of pressure. So when methane hydrates become unstable through climate warming or whatever, the methane has a long way to go to get out to the atmosphere. And most of what we see does not get out to the atmosphere. So those processes seem very unlikely to present some sort of methane catastrophe or methane bomb, although you hear a lot about it. And so my sense is, no, I wouldn't worry about that. But I think that there are feedbacks that could enhance methane emissions, let's say from tundra areas or boreal forest areas that might release quite a bit of methane, not hydrates kind of exploding at you. But and for that, the type of network that we're talking about would be a really excellent way to detect it as it crept in. And there's some evidence that it might be happening in some areas.
Just to expand on that a little bit, it in part depends on what you mean by abrupt. How big a signal are you going to need before you say, aha, that's in the, so I'll put my paleo hat on. There's only a couple times we think in the history of the Earth that there's been a destabilization of these methane class rates. Now, on the other hand, there have been numerous times that we can measure with ice cores that show that methane went up by 50 ppb or so in a relatively short period of time, less than a human lifetime. And maybe even down to maybe a couple of decades. If that's an abrupt change, the planet's quite capable of that.
We already had it here.
Yeah, we had it, right? We've done even better than that. But the natural feedback in that case is pretty clearly wetlands, and so I mean the committee did talk about. Let me back up. So we were asked to address future change, and we did talk about that. We recognize that if we wanted to really tackle future change, it's a whole other report, which I think, by the way, is tackleable. I would say in front of my National Academy friends, I think it truly is something that we should be thinking about in the not too distant future, taking that on. What is the future of greenhouse gases? We can actually do a pretty decent job of constraining the natural parts, and then you got to model the human side of things. But where methane's going to go in the future and how fast it can rise. I mean, right now, I would say the speed with which methane rises is more a function of what we human beings do to the system than what nature does right now. Nature will indeed feed some methane back to the atmosphere, but right now we're in the driver's seat in terms of shocking change.
Thank you. Tim.
Oh, my apologies.
Sure.
Yeah, absolutely.
So I wanted to point out that on some level the report is pretty limited in that it's focused, we call it methane report, but it's really the U.S. anthropogenic emissions of methane.
It's the title. Yeah.
Right. Right. So I was wondering, especially for the NOAA observing capabilities, we have some colleagues here from the satellite side of NOAA who are working on the methane product as we speak, but naturally it's on the more focused on the upper troposphere, not the near troposphere, near surface sensitive instruments that I could mention in the report. So I don't know if you could comment a little bit about just monitoring of methane in general or measurements. So it might not necessarily be feeding straight into some inversion model to get the emissions.
I think it actually, let me just address that briefly, and I know Steve wants to. I think it actually does feed into that. If you don't have a good handle on what the background is and how it varies, you cannot estimate what you're doing. That always has to be And one of the things that we talk about in the report, we stress in the report, is that the baseline monitoring system has to not only be maintained, but it should be improved, and it can't be subject to what it's been subject to for the last 20 years or so with continuing resolutions. So we have to be serious about that. So indeed, the satellite side of things, the baseline monitoring side of things, that's absolutely essential to be able to tell what you're doing on a national level or state level. There was another part to your question that I'm.
Oh, that's what I was talking about, just the background.
So I think there's a lot of ferment in the remote sensing area with respect to methane. Tropomi is just up. It's producing some data. I understand they still have some issues to deal with. Geocarb will have a methane channel. The GEMS will have a methane channel. So we're starting to see some sort of large-scale coverage that will go all the way down to the surface. Then, at the other end, you have people proposing and potentially flying things that look at 100-meter scales at facilities and whatever. And there are things appearing on the landscape in intermediate scale, a kilometer or whatever. So I believe that you're going to see a very, very big change there. And you guys who may not be flying those types of satellites would want to position your program to make optimal use of data like that, and it would be really potentially very powerful.
Ken?
Yeah, I actually have two questions. I wonder which one I should get first, but I'll try with the smaller one. So we got into this game off of Gabby's work and other work that GMD was doing, looking at emissions from natural gas production. We went to an early academy presentation. Somebody said, oh, you will never understand emissions from natural gas production by simply looking at wellheads or looking here. You need to do life cycle analysis. You need to look at the entire system in order to understand what the emissions are. And I got your picture that you showed and stared at that for a while, was fascinated. I had never realized the enormity of the natural gas system in the U.S. and all the components to it. So I guess my question is, this looked like a task for the Department of Energy. They should do it. Do you think NOAA could do a life cycle analysis of natural gas in the U.S.? Do you think we have the tools to do that, or is that a Department of Energy responsibility? Or
okay, so I'm glad that that's the short question.
That's a softball. Wait till you see the fast pitch.
It's the focus question.
Yeah.
So let me start out with terminology. So life cycle inventory. Life cycle is a type of inventory. And the difference between a life cycle inventory and what EPA puts out is as follows. A life cycle inventory counts the steel that goes into the ground, the pipes, all the way up to the life cycle of the well, the lifetime of the distribution system. So it's over a period. Life cycle inventories are essentially used to review options. Should we export LNG or not? Whereas inventories, but it's also a timestamp associated with it. Whereas inventories, on the other hand, are a timestamp, and your spatial resolution can be, a 1 kilometer by 1 kilometer, or an entire region, or the entire U.S., and the time period can be like that. So Nettle and Argonne have got life cycle tools. And the Argonne tool, ANL tool, is used a lot for transportation projects. Nettle life cycle tools are used for pipeline infrastructure divisions.
I don't know that everybody knows what Nettle is.
Nettle is the National Energy Technology Laboratory. So it's one of the national labs like Argonne.
DOE.
It's a DOE lab. So DOE has the forte and the strength in these life cycle emissions. What I think we were focusing on, all the experiments that we have, or projects that we've done with Rushnell's team, that's Gabby and Jeff Eichel and others, is focusing on an area, take an area, oil and gas producing region, and focus on all the infrastructure from the wellhead to the home that goes with it. So that is, in one way of calling it a natural gas system. I wouldn't call it a life cycle. I would call it the natural gas system. So So it's got the production segment, it's got the gas processing segment, it's got the gas transportation segment, and delivery at your home or our offices. That's definitely within the purview of NOAA or EPA or NASA, and I think that's the focus of this report. We didn't focus it on it from a life cycle perspective, but we focus it on a system perspective, a life system, the entire gas system perspective. So I do think, but DOE also has a role in this game because DOE funded the projects in Fayetteville and DJ, and I think that's where we come back and say no single entity or no single company has the strength to do everything together. That's why you need to bring different programs and partners together.
Yeah, we do have strength in the top-down. I noticed that DOE is also supporting top-down observations out of, not NETL, but the other energy lab that they have in Pittsburgh and West Virginia. They were looking at Marcellus shale. So I'm very intrigued by energy. They kind of flew below the radar. Not a lot of people knew about them and everything like that. But I was very intrigued by that, and whether NOAA could bring something to that aspect of it as a practical problem. Natural gas production in the U.S. is a major entity with major dollars associated with it, and this country could not exist without its natural gas. So I was just wondering if NOAA, as an honest broker, could bring something to bear on that problem.
It is. I mean, cause let me tell you my personal experience. I think the world of the NOAA team, Russ, Gabby, Stefan, Jeff, worked with them on multiple projects. And this report incorporates some of the key findings. I would say Stefan Schwitzky's work last year, the term mechanistic understanding is a term that he coined. And yesterday we had a question on what is mechanistic understanding. It's what basically you just don't fly around, but you also understand what, when, how went into the to the process to create this big emission. So I do think that you guys are already proven actors for doing this stuff.
Yeah, I think I got a good image of what the war is that you want, the challenge out there of a gridded system and everything like that. As a program manager, I'm looking for a few quick battles that I can win early on and get on and maybe win the war down the road. So lifecycle analysis, as I refer to it, looked like one of those battles that we could win, we could demonstrate our capabilities and do it. So that's why I was looking for something that we could get into quickly and get some rapid results on.
Well, there's one problem. It's not verifiable or falsifiable. So it's a decision tool, but it doesn't. You can't test it.
So life cycle depends on data that is extraneous to the inventory and also exogenous or part of the inventory.
It's really a model.
Well, maybe I need some help there, but that's why you guys are here. If I need some help, the other one that I wanted, if I could ask just a quick one and everything like that. The first recommendation had NASA working with NOAA, and that's we work with NASA for ages and everything like that, so we know how to do that. We have not worked extensively with DOE or with EPA. That's a challenge, and you could see that at yesterday's body language. That's going to be a challenge to work with EPA and to be that. That's going to be a slow. That is the war that I referred to, and I don't mean that it's a battle. I mean it's a challenge, a real challenge to do that. Do you think that and the other one that I wanted to bring out, Antonia is here now, is that in addition to national satellites, we also have NOAA satellites that could be brought to bear on that. Are there usable products that could be developed, dominated by top-down observations products now that we could produce with NOAA and NASA working together? Their satellites are in situ observations. Are there actually useful products that we can produce?
Well, I really think so, but maybe I'm not sure about the current satellites, but starting with Tropomi and then Geocarb, I would think that there would be a lot of opportunities there. And you could combine it, so there's also Tempo, which is looking at your pollutants. If you start thinking in this multiple species space, they start to reinforce each other. So Those are both geocarb and tempo are geostationary, so they'll image the continental United States several times per day, wall to wall, and total column, so all the way down to the ground. And I think it's a science study. It hasn't been done to say what would be the best way to really link these two together. But if you do that, you will get a big payoff.
Yeah, I'm going to say this again. I would hope we weren't discounting the role that the JPSS series could play in there. You can get trace gas observations from those satellites too, and some of the NASA satellites are now transitioning into JPSS-1. The Earth satellites that were put up are now more than a decade.
Well, I'm less familiar with what's on there. I believe there were like thermal emission things. Yeah, so those are upper troposphere.
Maybe remember maybe 10 years ago we did some study, and this was in between the airs.
Airs, yeah. Mm-hmm.
So, and that was also for the heatful campaigns.
That's correct. Yeah.
And my question actually would be, what are the lessons learned from there that you can pass along such that we can derive conclusions on what to do with
So I would go to Jim's answer, which was correct, which is those things can really help us understand the backgrounds, what's coming across the Pacific. So that's kind of a different focus from what we did. This by task was not studying the Pacific, it's studying the continental United States. So yeah, there is definitely a role for that, but I think if you ask what do I learn by studying 10 kilometers over the United States, if you're not learning about the United States. But you do learn about things that are important. So I didn't mean to discount this as being useful, but more in the line that Jim.
Actually, that leads to a question that follows up on Ken and Monica. I noticed that the discussion here seems to be very focused on the United States, but some of the figures that you've shown, certainly the emphasis that I see here seems to be of climate focus. Is that correct or no?
Source,
yeah.
The reasons for monitoring methane include climate, but it's not
only. Okay.
The only,
Yeah, the satellite perspective, obviously would be more objective climate usefulness, I think, right? Because the global coverage that you would get, it's more global, and so that's I think of a better use there, I think, right?
I think if you sat down 10 scientists and say, why should we study methane? Number one reason from 8 of them would be climate. But there'd still be the 2 who talk about ozone production or talk about health impacts or other reasons. Because methane does indeed have
At least one was on your committee.
Huh?
At least one of those was on your committee.
Yes. Yes.
So I just wanted to do a quick time check because I know some of our distinguished guests have to cut and run for the airport this afternoon. So we only have about 2 more minutes, so maybe that leaves time for one more question. So I'll just look around the room to see if anyone has anything else they would like to ask or comment. I haven't received any questions from our online viewers. I hope that means they didn't have any and they weren't trying to get them to me. I've been monitoring the windows here. So maybe I'll turn back to you then and to the committee members to see if you have any closing remarks or closing thoughts or points that you'd like to share.
Other than I think we end where we began by thanking NOAA, thanking you for the opportunity to come and talk to you, thanking NOAA for the support of the study. The committee obviously thinks this is a very important thing. I personally think that this is if we follow through, if the U.S. follows through on this action, I think it could be transformative in terms of our relationship with the environment, with the planet. I think we do need that transformation. I'm looking for bold action. And when I say bold, I mean bold. Very good.
Just to say the report is available free online, so download if you like. And we're more than happy to do briefings and other studies. So if there are other places or other folks that you think that would be useful to hear about the report, we're happy to set that up. I'm sorry, smiling.
I think Katie said it.
Yes.
It's also coming out. Yep, we'll have a brochure that we can, popularize the report with the, there's so much popularize the report, but popularize the activity, that it's focused on.
And since this is our last briefing on this, I think, you know, I can say, and the others who were involved in the last couple of days can chime in as well. We were very heartened by the interest and enthusiasm from all the groups we talked to. We don't normally go to agencies like we did with this report. So the EPA was very interested. It was a really interesting conversation.
I'd love to hear that.
We could
over a beer,
download over an amber liquid at some point. But it was. I thought that the interactions we had with the House and Senate were also quite. I mean, given the fact that they were on recess, the staffers were there and they were interested and they asked really good questions. The committee was, I think, very impressed. We were, you know, honestly, we were concerned that report on methane right now might be received with crickets and a dull thud, but that did not happen at all.
Well, I mean, I believe that NOAA has a great resource in its atmospheric composition scientists, sometimes unrecognized. I remember I went to a meeting and the first question that came out of me is, why are you here? Does NOAA have chemists?
It's like, does Harvard have an engineering school? I've heard that one.
So, and we do. We have great chemists in NOAA, sometimes overlooked.
Well, thank you so much.
Dr. White, on behalf of NOAA and the Climate Program Office, we thank you for your time. Everyone have a great afternoon. And that concludes today's webinar.
Thank you.
Thanks for having us.